Lecture number 22. So, today we will be looking into carbon-carbon composite, which is one of the star requirement in aerospace industry, and automobile also slowly have started taking care of this carbon-carbon composites. Carbon-carbon composites are wherein which the matrix is a carbon, the reinforcing agent is also made out of carbon. So, in this lecture we will have a content introduction to CCC, then we will have different matrices, then we will see the processing techniques, advantages and applications. These will be the content. So, here a composite, you are trying to use a fiber which is made out of carbon material. Then you will also have a matrix which is made out of carbon material. These two put together we try to get a carbon-carbon composite. The function of the filament here is to give high strength, high stiffness, and it also tries to give you low density. The matrix, it has to have good shear strength property and low density. So, you see here this is also low, this is also low. So, naturally the composite what we get is going to have a very low density. So, it will have good shear strength property from the matrix, high stiffness and high strength comes from the fiber what we use. So, we will use a fiber which is made out of carbon. So, it can be a single wire, it can be a matte, a 2D, or it can also be a 3D. So, depending upon the requirements we choose a proper reinforcement. Matrix is made out of carbon and then we try to make composites. So, when I said matrix is made out of carbon, so quickly, since we have studied about the ceramic matrix composite, what should come to your mind is we will try to use a polymer, we will try to do pyrolysis and we get converted into carbon. So, this should be the basic thought. We will see the process whatever we have lined up here. So, matrix, the matrix can be polymer matrix composite, metal matrix composite, ceramic matrix composite. The most interesting and which is finding lot of applications are carbon-carbon composites. Then we also have bulk metallic glass composites. This is the next field which is coming up, which is called as BMG composites. In this lecture we will more focus towards about CC composites. So, a matrix, so what are the different types of carbon matrix? They are thermoset resins can be thought of, phenolic resins, you have fluorine resins, then oxidized pyrostyrene we have, then we have pan resin, then we have polyvinyl leadine chloride. So, this and then etc. You have many more resins which are available. For these are all the possible matrix for carbon. So, you in the carbon fiber can be made out of rayon based, can be made out of pan based, can be made out of pitch based. So, rayon, pan, pitch, these three are the starting materials which are used for making carbon fiber. Even today it is a state of the art, technologies are available only with few people for making highly pure carbon fibers. Up to 92% or 95% it is easy to make pure carbon fibers, it is easy to make. Anything above that it is IP rights, it is a proprietary item. Only very few companies across the globe hold the rights for making this carbon fiber. They make it out of rayon, pan or pitch. These are the set of matrices wherein which this can help in making a carbon matrix. So, matrix reinforcement put together forms a carbon-carbon composites. So, it is a family of complex advanced materials that consist of carbon fiber embedded in a carbon matrix. So, carbon-carbon composites are those special composites in which both the reinforcing fiber and the matrix are made out of pure carbon. They are made out of woven mesh of carbon fiber. They are used for very high strength to modulus of rigidity they get, and here they can withstand up to 3000 degrees Celsius. This is very important. This property makes CC composite quite usable in aerospace industries. The space shuttle which comes back are nowadays made out of carbon-carbon composites which are light in weight, which can withstand very high temperatures. And apart from that, lot of filaments which are used for very high temperature furnaces, they are also nowadays made out of carbon-carbon composite because they withstand very high temperatures. So, CC composite can be tailored to meet whatever is the customer requirement. And today what has happened is they put carbon-carbon fiber and then they have another material up and down. So, now CC composite is used also as a insert. They are added in between sandwich. So, this assume this is a metal. So, you have two metals and then in between you have carbon-carbon composites for required application. Again, as I told you here, it can be in the form of a woven mesh. So, this is a 3-dimensional version. So, this is a preform wherein which is made out of carbon fibers and through which the carbon matrix is infused. The carbon fiber which is used in the CC composite are tailored to their mechanical properties of the final structure. So, for this the carbon fiber plays a very important role. So, carbon fibers are having very high strength modulus and intermediate modulus fibers are also available in this in carbon fiber. So, this is a human hair, this is a carbon fiber. Typically the human hair goes from 60 microns to 100 microns. This is the size of a human hair, it varies in this range. But you look at it, this will be approximately 5 to 10 microns. So, this is how the carbon fiber is made. So, here is a comparison between human hair and carbon fiber. The reinforcement, these fibers are the carbon fibers first are prepared from pitch or pan. The carbon atom bonded together to form a long chain. So, in pitch or pan what we do is we try to take it, the carbon atoms are bonded together to form a long chain. This super strong material that also extremely lightweight is a carbon fiber. They have 5 times stronger than steel, 2 times stiffer and about 2/3 times less weight as compared to that of steel. So, this is a carbon fiber. So, fiber, so you see this is an interface, right, fiber interface and this is the matrix. Okay. Carbon fiber has very good mechanical properties. So, how is the carbon fiber prepared? So, in a pan process we take pan and then we try to stretch the fiber, pass this fiber through a thermoset and then we try to carburize it, then graphitize it, then we try to do a surface treatment, then epoxy sizing we do and then finally we bind it in a spool. So, about 90% of the carbon fiber which are produced today are made out of pan process. The 10% is made from rayon process and this is a very well established process. So, because of this carbonizing and graphitizing we need very high quality processing here. So, basically it has to be a furnace and then there has to be a gas carrier media which is there. So, these two should make sure that a proper output is given. So, rest all treatment are straightforward. So, pan you passes through spools. So, the carbon fibers are stretched. So, they are brought to high strength and then it undergoes in a thermoset, it expands and the series of rollers, then carburizing, then graphitizing, then you undergo this surface treatment, epoxy sizing and then you try to do with spool. So, the processing of carbon fiber. So, we have carbon fibers. So, these are carbon fibers which are there. You can see rough lamellates. So, these are carbon fibers which are with rough lamellates. You can also see with a smooth lamellate. You can also see with isotropic properties. So, these are the different processing of carbon fibers. So, with this you can see these are the microstructures which are made and then a carbon with lamellate structure, laminar structure, this is the smooth structure and isotropic structure is possible. So, when you talk about carbon matrix, the carbon matrix in CC composite basic function is to transfer the mechanical load between the fibers. It has to bind the fibers, These two are well known. So, it acts as a binder to maintain the alignment of the fibers and the fiber bundle, at the same time isolate the fiber from one another. So, this is the basic function of a carbon matrix. The other important criteria for the selection of a polymer precursor to form a carbon matrix should be that it has to have a very high carbon yield. Why is that? Because I have put a big list of polymers wherein which you try to do a proper processing, it gets converted into a carbon matrix. So, now what should be the selection criteria? So, that is what we have listed it here. High carbon yield it should give, it should have as minimal shrinkage during pyrolysis process, it should be amenable with all type of polymer matrix composite when it follows a route of resin transfer molding or filament winding. It should use low solvent content, it should have the highest high degree of pre-polymerization with low viscosity, it should have the ability for multiple sources, it should be low cost, its pot life and the storage lifetime should be very long. So, these are the conditions which are put in front of before choosing the polymer precursor. If you look at it, this is a composite, carbon-carbon composite, this is a carbon matrix, and these are the fibers which are used. If you generally the CC composite has a nomenclature. So, this is the CCM, it is written as it is carbon-carbon composite, it says 1 or 4. So, 1 stands for continuous fiber, 4 stands for chopped fiber. So, you can put that signature digit there. Then 90 is the orientation, 0, 90, the alignment can be put as 90, 45, 30, whatever it is. So, this is 0, 0 means 2D random, and if you put 90, it is 0, 90 orientation. You can also have 45. This C is this digit represents the heat treatment temperature. C means it is processed at a temperature between 2000 to 3632 degree Fahrenheit. If you put M, then it is 2500 degree Celsius to 4532 degree Fahrenheit, or it is 2000 degree Celsius, M is 2500 degree Celsius. So, this H represents purity, how pure is the carbon-carbon composite. Regular grade, H is purified grade, SH is super purified grade. So, these are the grades. So, CCM composites this is a signature which it follows. The first digit talks for reinforcement, next digit talks for alignment, next digit talks for heat treatment, and the last digit talks for purity of the composite. So, you can see here in plane and cross plane. So, here this is the product. Okay. So, you can see in plane, and this is also in plane, this is cross plane. So, you can choose this in plane and cross plane depending upon your requirement, or depending upon your final product, you choose whether to go for in plane or you go for cross section. So, in plane and then you have cross section. So, structures are there. So, what is the advantage of carbon-carbon composite? It is very light in weight. You look at it, it is 1.6 to 2 grams per centimeter cube. It has very high strength at very high temperatures. For example, cutting tools and all, you look, they do not need strength at room temperature. Strength at room temperature, strength at high temperature. Okay. This is very important. Today our requirement are strength at high temperature requirements. Room temperature, you can see the strength will be good, hardness will be good, but very high temperatures, the strength, the material gets deformed. Moment it deforms, then it loses its functional properties. So, high strength at high temperature is another big advantage for CC composite in a non-oxidized atmosphere. Then it has to have low coefficient of thermal expansion, it has to have high thermal conductivity, and it also has to have high thermal shock resistance. When we look at ceramic matrix composite, we said two properties are very important. One is the toughness property has to be enhanced, or fracture toughness property to be enhanced. That is why we go from ceramics to ceramic matrix, and the next is high thermal shock resistance for a ceramic matrix composite. When you go for carbon-carbon composite also, we keep this as one of the biggest criteria, or this is one of the biggest advantage for choosing carbon-carbon composite. It has very low weight, it has very high strength at high temperatures, it has very low coefficient of expansion, it has very high thermal conductivity. Today people are looking forward for heat exchangers made out of carbon-carbon composite. But what are the disadvantages? The disadvantages are the fabrication cost is extremely high, because all the processes need furnaces. These furnaces should have gases in the absence of oxygen, that is one. The temperature what it operates should be very high, which cannot be normally used in a furnace where the heating coil is made out of steel or tungsten. Okay. Next, the process leads to lot of porosities. This process is followed is very similar to that of ceramic matrix composite, we will see that. Then it has poor oxidation resistance. So when it is done, when there is a few trace of oxygen, immediately the carbon-carbon composites, the carbon matrix loses its functional properties. It has very poor interlaminar shear strength. So we have to be very careful before using it for structural applications. It has low oxidation resistance, it reacts with oxygen even as low at 500 degrees Celsius, it reacts and it forms different compounds. So the major disadvantages: cost, porosity and oxygen presence puts this carbon-carbon composite into still a very difficult component for manufacturing. So if you look at it, Europe uses the North America uses maximum of 35, followed by Europe, which they use carbon fiber to a large extent. Then we use Japan uses 15% and the rest of the world uses 20%. So this is what is the consumption of carbon fiber in the global market. So slowly it has been used in Asian countries. So the application of CC composites are: it can be used for a braking system where there is going to be very high temperature, it can be used as a refractory material, it can be used as a hot press die. For a turbojet engine components, they are today made out of carbon-carbon composite. So wherever you can replace ceramic matrix composite, we go for carbon-carbon composite. Ceramic has a fracture toughness property, so here it does not have that. But however, making CC composite is also a challenge. So heating elements are made out of CC composite because they can withstand very high temperature. Missile cone tip, because when it enters inside or when it goes outside the atmosphere, there is a huge friction coming out. So missile cones are made out of cone tips are made out of CC composite. The rocket motor throats are made out of it. Leading edge of space shuttles are made out of it. Heat shieldings are made. X-ray targets are made out of it. Aircraft this braking system is an automobile. Today even in bikes people have started using CC composites. Aircraft brakes, re-entry vehicles, biomedical implants, engine piston, because very high combustion if you want to have. So the temperature which has to be withstand by the piston should be very high. So now you started using CC composites. Then we have electronic sinks and other automobile and motorbike bodies are made out of carbon-carbon composites. If you look at Boeing Dreamliner 787, the composites are 50% made out of this, and then we will have carbon-carbon composites. Carbon laminate composites are used in the tail region. It is also used in the wings. The carbon sandwich composites are again used in the tails and as well as in the wings, we can see. And then it is also used in the turbocharge. The casing is all made out of it. So the components that are used for uses the composite structure are almost the fuselage is made out of composite. Some are made out of glass fiber also, but now they are replacing it with carbon fiber because of lightweight. Then upper and the lower wing skin are made out of it. Radome is made out of it. Radome is in the front portion. The wing flap, elevators and the ailerons are made out of it. The vertical fins and the horizontal stabilizer. So these are the horizontal vertical stabilizer which are made out of it. So now the complete plane are moved towards carbon-carbon are made out of carbon fiber composites, and they are also slowly moving towards carbon-carbon composites. So if you look at LCA air frame, these LCA air frames, they are made out of carbon composites. You can see these are the portions which are made out of carbon composite, and slowly they are trying to replace this carbon composite with carbon matrix composite. So, here it was carbon composites where it was not carbon, that means to say here only fiber was used and polymer was used, and slowly when in the high temperature engine and other places they are replacing this carbon composite with carbon fiber composite. So, significant weight reduction is there, significant reduction in the part count also, since it is going to composite, complex shapes can be made and integration of inserts in the parts can be made. So, number of parts are gone down. So, the fasteners are reduced, because basically when you use composite materials you can think of using adhesives rather than making a hole. So, when we look into machining, you will understand when you drill a hole there will be a lot of delaminations coming into. So, nowadays it has gone to adhesion bonding. Then fatigue life is improved because we try to choose proper interface between the matrix and the fiber. So, we try to enhance the fatigue life, the crack growth can be arrested, and to a large extent the signatures are reduced in the LCA frame. So, this is the carbon fiber composites, 45% it is tried using. So, this is the rocket nozzle tip which is made out of carbon composite. So, this withstands very high temperature. So, a space shuttle nose tip are made out of carbon composites, thus of very high temperature. So, now slowly let us get into the fabrication methods of making CC composites. So, here there are 4 methods which are predominantly used, okay, 4 routes. Sometimes a combination of the 2 routes are also used. See, in manufacturing there is nothing called as a unique solution. So, depending upon the availability resources, depending upon the output required, a combination is always thought of and we try to get the required output. So, here we have the 4. So, one is impregnation and pyrolysis using thermoset resin, impregnation and pyrolysis using thermoplastic pitch precursor, and then we have a CVI route, we have CVD route. So, fabrication method, here is a schematic diagram which is given. So, the schematic mechanism of pore filling and pore blocking by liquid impregnation and CVD process. So, here what we do is these are the pores, pore entrance diameter, okay. This is a cross section of a single pore. So, this is pitch impregnated. So, what we have is this is pitch impregnated pore is there. So, then what we do is we try to graphitize this pitch coke, we try to do it. So, what we do is we take this pitch impregnated, then we heat it to 2500 degrees Celsius. So, then the resin is impregnated, then this pyrolytic carbon is formed, and then the gas impregnation early stage is like this, okay. So, then what we do is graphitization of the pyrolytic carbon happens, and then after heating at 2500 degrees Celsius, there is a graphitized pyrolytic carbon which is getting formed, and the gas impregnation final stage after heat treatment to 2500 degrees Celsius, we make a carbon composite by this process. So, here is a pore, this is a cross section of a pore. So, this can be done by 3 routes. So, one, we try to put the pitch here and the pitch is impregnated here, right, and then what we do is here we try to graphitize the pitch coke. Then how do we get this done? We heat it to whatever it is, we heat it to 2000, we heat it to a higher temperature 2500 degrees Celsius, then it forms like this, and then we try to the pitch coke is formed. Then here what we do is we try to use a cured resin, right, and then this cured resin is graphitized pyrolytic carbon is pushed into, so we get something like this. So, then pyrolytic carbon is like this, and then this is the early stage of impregnation, and this gas impregnation final stage after 2500 degrees we get the required carbon composite. So, the fabrication method, generally each of the 3 processes are carried out at a temperature between 800 degrees Celsius to 1500 degrees Celsius. The final heat treatment goes up to 3000 degrees Celsius. These 3 methods lead to different microstructures in the composite, partially because of the difference in the method of the formation of carbon from the 3 different types of precursors, but mainly because of the formation of carbon forms having different structures and properties for different precursors. So, these are the three precursors. With this precursors we are trying to get different types of CC composites. The thermostatic resin based processor for carbon-carbon composite. The resin are usually dissolved in an organic solvent with a catalyst / a curing agent before infiltration. The resin in the impregnated composite is cured and then pyrolyzed by heating it to a temperature of 350 to 800 degrees Celsius. Frequently, hot pressing at high pressures up to 10 megapascals and the temperature from 150 to 350 degrees Celsius for a period of 10 hours it is done to get intense density in the curing process. Then the final pyrolysis of the composite is subsequently graphitized at 1000 degrees Celsius. We get a CCC composite. Okay. So, in this if you see very clearly, time, pressure and temperature are very important, and then here in the absence of oxygen is very important. So, if you look at it, following is a flow diagram for CC composite using thermoset resin. You have a fiber preform. This is resin is getting infiltrated into it, then we do a curing. The next stage is you get a pre-peg, then stacking of the pre-peg, you do curing. So, pre-peg is where already polymer is fitted into the resin. So, you have a continuous fiber, then resin impregnated, we do filament winding and then we do curing. So, when all these things are cured, you go to pyrolysis. So, pyrolysis is done up to a temperature of 800 degrees Celsius. Then what we do is, moment the pyrolysis is over, then there might be some pores or some gap in between. So, again what we do is we try to do a resin infiltration, and this process is repeated multiple times until you get the final required dimension, strength or thickness or whatever it is. Then once it is done, then finally we do one more heating from 1000 degrees to 3000 degrees Celsius to get the required output. Through this processing route, we try to get a carbon-carbon composites manufactured using thermostatic resin. So, preform, pre-peg, and then we use continuous to get the carbon-carbon composite made. So, we can also use thermoplastic pitch based processing. So, for carbon-carbon composites, so the pitch impregnated preform is subjected to two pyrolysis, carbonization in an inert atmosphere to convert the organic compound to coke, and a high temperature treatment at 1000 to 2000 degrees Celsius for graphitization of the coke. So, first it forms pitch into is converted into organic compound into coke, then we try to do this coke to get graphitized of this coke to get the required output. So, the densification process is carried out at atmospheres at atmospheric or at reduced pressure, is repeated several times to get the desired density. It is more efficient process. The coke yield for pitch increases from 50% to 80% by weight. The pressures which are used are 70 megapascals. The pressures are also very high. So, this is what is the route flow chart for making it. So, fiber is taken in a preform, okay, and then we put the molten pitch, infiltration is done. Fiber preform, molten pitch infiltration is done, then pyrolysis is taken care. The molten pitch infiltration happens, then we do one more round of pyrolysis, and we keep adding, repeating these steps n number of times, and then finally we do a final treatment at this at 2000 to 2200 to 2700 degrees Celsius to get the required output. By this way we try to make carbon-carbon composites. So, basically the resin is taken to a very high temperature, it is graphitized to get the required output. So, this is for thermoplastic pitch based processing. The next one is chemical vapor infiltration process. In chemical vapor infiltration process, the gaseous precursor is infiltrated into the fiber preform. This is driven by either diffusion process or it is imposed by a external pressure. So, either you push it or there is some phenomena which sucks it, capillary action, you get it done. The deposition filling fills the space between the fiber forming and the composite matrix in which the resin is the deposited material and the dispersed phase is a carbon phase. The chemical vapor infiltration is a very similar process to that of chemical vapor deposition, which we have seen in ceramic matrix composites. So, we use the precursor gas, then we use a carrier media, carrier gas, and then what we get is CVD, and this CVD is done on a substrate. So, on a substrate or on a fiber we try to get the required output. So, this is CVD process or CVI process here. So, what is the difference between the previous process and this process? In the previous process what we do is we take a fiber, we take a molten pitch which is infiltrated. So, all these things happen somewhere close to room temperature itself. But here in CVI what we do is we try to take the precursor, the precursor is a gaseous precursor which tries to pass through the resin fiber. So, as I told you last time in ceramic matrix composite, we have a isothermal CVI process, we have a thermal gradient CVI process, we have a pressure gradient CVI process, we also have a rapid CVI process for making carbon-carbon composites. So, here through this the reactant gas is passed through, here is the preform carbon fiber which is kept, this gas goes into, reacts and then makes a carbon-carbon composite. So, when it reacts, if whatever happens is only at a nascent stage or in a green stage, then after this it has to undergo 1 or 2 times of more graphitization, so that the carbon-carbon composites is formed. And here these vapors are infiltrated at regular intervals, so that you try to have a proper densification of the carbon-carbon composite. So, these are the induction coil for heating, this is a hot region, preform is used, and this is a graphite holder, so that the graphite can withstand very high temperature, otherwise they would have gone for a metal or a steel one. So, and here in the bottom they use a water jacket and then for cooling. So, what is the major advantage? Low fiber damage happens here, then highest purification can be done, low infiltration temperatures are required, enhanced mechanical properties can be done, good shock resistance happens, increased creep and oxidation behavior comes, interface can be deposited in situ, we want to enhance. What are the disadvantages of this process? It is a slow process, it can take even several weeks to have it. It has a porosity is always part of the product. So, this porosity will try to give a very less or this will have to compromise a mechanical property. It is capital intensive. In CVI process, this is how the CVI growth mechanism is there. You have initial fiber which are arrays, these are initial fiber arrays, these are initial matrix infiltration happens, right, and then what happens is this is first, let us take this is one stage, and in the next stage you keep on pumping it second time, third time, fourth time. So, you see that this initial matrix which was infiltrated, the thickness increases, and we are talking about the residual pores of 10 to 15%. These are the pores which are there because completely this portion is locked. So, once it is locked, the further gases cannot go through. So, this portion is the residual pores which is prone to happen here in CVI process. The best pore, that means to say the lowest porosity what you can get is around about 6%, which are reported in the research publication, but generally it is 10 to 15%. So, what is isotherm, which we were discussing? There were 4 different types of CVI. So, what is isotherm CVI? Isotherm CVI is the most widely used process and it is very similar to that of a ceramic matrix composite. So, here the fiber preform are heated in a CVI reactor up to a infiltration temperature in the range of 800 degrees to 1200 degrees Celsius. So, the fiber preform is heated, reactor up to an infiltration temperature where the temperature ranges from 800 degrees Celsius to 1200 degrees Celsius. A slow deposition rate can be achieved by operating the reactor under reduced pressure and a low temperature of 1050 degrees Celsius. So, this is a isotherm CVI. So, you have a process temperature of 1050 degrees Celsius, the pressure is 50 millibar, the flow rate is 2.2 SLM, and then the H2 is to MTS ratio is 10:1. So, here this is an isotherm, we push in gas inside the furnace and we start using it. So, if you look at the density evolution of CVI, so over a period of time we see that 100% the densification keeps on increasing. So, the process duration you see here, it is almost 355 hours it is done, so that you try to get a final shape. So, this is the product which was supposed to be made. So, for making this process it takes 355 hours. So, the initial preform was around about 0.7 kgs, the final preform mass was around about 4.88 kg, around about 5 kgs. So, there are 50 steps which are involved. So, every time what we do is we keep on pushing gas inside. After every after one cycle we try to push the gas once again, and then we start improving the densification. So, you can see the densities which is increased from 300 to 2135 millimeter cube. The thermal gradient CVI process, in order to reduce the processing time. So, if you see here, it takes isothermal, it is around about 355 hours. So, in order to reduce the time, what we do is the thermal gradient and a pressure gradient has been developed. So, in thermal gradient CVI is normally performed as a cold wall CVI process. This process is very suitable for large carbon composites such as the rocket nozzle are made out of it. The fiber preform is placed around a mandrel here, and which is heated. The outer surface is exposed to a cooler environment because the proximity of water cooling is possible here. So, this is what is the schematic diagram for thermal gradient CVI process. This is a graphite mandrel. So, you place your preform, the gas is flown from the top. So, the heating is maintained in the furnace. So, this is a fiber preform. So, this is a schematic diagram of thermal gradient CVI process. The cooling jackets are here. You can see the induction is given, these circles are induction, and then after that you will have cooling. Then you have a preformed fiber, carbon fiber preform is the reinforced preform is there. You have a mandrel on which the preform is wound. So, now you pass gas through it. So, you try to get the carbon getting infiltrated into the preform. So, you produce a carbon-carbon composites. So, you also have a pressure gradient, which is a small variation, modification of the isothermal CVI process. So, here a carbon fiber is placed in an isothermally heated furnace with an outer graphite tool, which only leaves a small gap for the forced gas to flow, forced gas of the precursor to flow through. The pressure difference that forces the gas flow through the pores is created across the walls of the structure. The process is also limited to the production of a single or a simple shape only done here. This method may not be suitable for commercial production of CC composite parts for a large area. So, this method is not used. So, the schematic diagram is seen here. So, you have, this is a fiber preform, this is the gas in, this is a gas out. So, you have heating coils and here it is airtight, so that you try to make simple geometries out of it. So, there is a pressure gradient which is maintained such that you get the CVI done for making a carbon-carbon composite. The next process is called as rapid CVI process, a rapid CVI process technique developed by France. This is still in a very nascent stage, can be rapid for industries wherein which the densification which is done is very good. In this process, the precursor of carbon fiber preform acts as a carbon susceptor and is fully immersed in a liquid hydrocarbon such as cyclohexane or a toluene. So, it is immersed inside and then we do the process. Out of the two hydrocarbon, the carbon yield is higher at toluene. The complete densification of CC brakes can be achieved within 10 hours by this process. So, what we do is we try to take a porous carbon fiber preform which acts as a susceptor and it is fully immersed inside a liquid hydrocarbon, and then you dry it, you get the process done very fast. So, the other one is chemical vapor deposition. So, it is infiltration, here it is deposition. Infiltration is pushing through, deposition is you deposit on top of it. Okay. So, here the preparation of CC fiber preforms of a desired shape and structure is done. The densification by the densification of the composite by CVD techniques are pretty good. The infiltration from the pressurized hydrocarbon gas is around 900 degrees to 1200 degrees Celsius. The gas is pyrolyzed from the deposition on a fiber surface. The process duration depends upon the thickness of the preform. The heat treatment increases the modulus of elasticity and strength. This process gives high strength and modulus of elasticity when we use a CVD process. In a CVD process, we use gases and then we use a carrier gas. It is passed through a furnace and wherein which there is a maintained temperature of 720 degrees Celsius. This is a quartz tube and there is a quartz boat which is there, wherein which the sample is given. By CVD, the carbon is getting deposited on the fiber and we make a carbon-carbon composite. In this process, this is quite slow, and second thing is here there is a possibility of other impurities coming formed. So, there has to be a proper control on the output. The limitation of this, the hydrocarbon gas which is infiltrated into the interfilament surface, and it also it forms an interfilamental surface and a crack. Sometimes these gas deposits on the outer shell and leaves lot of pores. The infiltration and the densification is required. It takes a long time to do this process. So, if you look at the properties of the CCC composite, it has excellent thermal shock, low coefficient of expansion, high modulus, high conductivity, low density, high strength, high coefficient of very low coefficient of friction, high resistance in non-oxidized atmosphere, high abrasion resistance, electrical conductivity and non-brittle fracture. These are some of the properties which are good for carbon-carbon composites. So, if you look at temperatures, polymer matrix composite, it can withstand thermoset can go up to 300 or 400 degrees Celsius, this can go up to 500 degrees Celsius. When you look at metal matrix composite, it can go from 400 degrees Celsius, it can go depending upon your matrix requirement, it can go up to 1000 degrees Celsius. This is a service condition where it can work. Ceramic matrix composite, it can go up to 1300 degrees Celsius, it can be silicon nitride, silicon carbide. Alumina can go up to a slightly higher temperature of 1400 degrees Celsius. Look at carbon-carbon composite, it can go up to 1500 degrees Celsius service condition easily, a temperature around, and when you do a graphitization, when it is graphite, it can go up to 2000 degrees Celsius. So, this makes it a very viable matrix for high temperature applications. So, if you look at specific strength at varying temperatures, you can see that carbon-carbon composite, the specific strength is almost constant up to 2000 degree Fahrenheit. Whereas aluminium, there is a decline. Titanium, you can see over a period of time it is declined. Inconel for slightly higher temperature, and nodular iron with also there is a decline which happens over a period of time. So, the carbon-carbon composite maintains the strength, the specific strength to a high, for a very high temperature as constant. So, it also depends upon the orientation. If you have, this is a flexural strength for short fibers, for cloth type, and then for roving type plus minus 45, roving type plus minus 15, unidirectional carbon fiber we use, and then we try to have multiple orientations. We can go have a flexural strength as high as 700 Newton per millimeter square. So, if you look into it, this is as a climax for this carbon-carbon composite. So, if you see here, carbon fiber reinforced plastics strength versus temperature, the carbon fiber falls here, and moment you convert this matrix into a carbon. So, this is carbon fiber reinforced, this is carbon fiber reinforced in a carbon matrix. You can see here it works very nice from 1000 to 2000 degrees Celsius. It works excellently well. There is no compromise in strength, and in fact you see here, this is the major advantage of carbon-carbon composites used in very high service temperature conditions. With this, we come to an end of this carbon-carbon composites fabrication, and we have seen different properties. So, predominantly here we use thermoset matrix, thermoplastic matrix, then we use CVI. In CVI we have seen 4 different variations to reduce the cycle time and to enhance the quality of the output. We can also do exclusively CVD, but there is lot of limitation in this process. So, that is why we do not use CVD to a large extent. We follow only CVI process to get the carbon-carbon composites. Thank you very much.